Hello, so in this video we're going to talk through something called transformations of graphs. Now, the idea of this topic is that you should know some kind of fundamental, basic graphs, and you should understand how you can transform those graphs to get them to look slightly different. So as an example, if I just give you a straightforward y equals x squared graph, a straightforward parabola, and we all know hopefully that that's y equals x squared, by applying some certain transformations to this, so it could be a shift, could be a reflection, it could be a stretch, you should be able to get a graph that follows the same kind of shape, but perhaps it looks slightly different. So for example, you might get a graph that looks something like that instead. So it still has the same characteristics as the original y equals x squared graph, but perhaps it might be shifted, perhaps it might be stretched, perhaps it may even be reflected as well. And the important thing is that we need to understand what those transformations are doing. So before we get started, I think we just need to remind ourselves of some certain graphs. Now, some of these you will know and you'll be able to draw like that. Other of them you might need to think about a little bit more. So I'm just going to give you all of the graphs that you kind of need to know. So let's just first of all start off with a nice straightforward easy graph. Okay, let's start with something like y equals 2. Okay, now just remember, when I write something like this down, y equals 2, it is basically saying, find me the set of points which have a y coordinate of 2, okay, and then join them all together. So I don't want you to think of a line, like a graph, a line, as just simply a line. I want you to think of it as a infinite set of points which all follow a set of rules. In this case, the rule which we're following is that y is equal to 2. So if I draw myself a set of axes out, so have a look here. Draw my axes, okay? Now I just need to connect together all of the points which have a y coordinate of 2. Well, hopefully fairly obviously, the set of points which have a y coordinate of 2 will just be a flat horizontal line and they all have a height of 2, okay? Because are you happy that, for example, this point here might be 1, 2, this point here might be 2, 2, this point over here might be negative 1, 2, perhaps this point here might be 0, 2, and this point here might be negative 2. 2. Okay, so basically I'm just connecting together all of the points which have a y coordinate of 2. Okay, and we tend to draw all of those points just as a single continuous line like so. Okay, so hopefully you realize that when you draw a line, when you draw a graph, okay, you're not actually drawing a line. What you're actually drawing is a set of points which all follow the rule which you've been given. In this case, find me all the points which have a y coordinate of 2. All right, similar kind of thing then. Okay, if I go x equals 4. Okay, so this says, find me all of the points which have an x coordinate of 4. So I don't care what the y coordinate is, as long as the x coordinate is 4, that rule has been satisfied. So let's have a look then. So if I draw myself out a set of coordinates, Cartesian coordinates, then I can basically say that the points which have an x coordinate of 4 will be something like that. Okay, and that will be 4 there. All right, so basically all of those points which I've just drawn in that line, okay, will all have an x coordinate of 4. So you notice the difference between the top graph with y equals 2 and the bottom graph x equals 4. And it's that if we're talking about a y coordinate of 2, so y equals 2, we basically get a horizontal line. Okay, so if I'm drawing the graph y equals something, I should just expect a horizontal line where the height of that line is dictated by what my y is being told as. Okay, whereas when I'm talking about x equals 4, I get a vertical line instead. So y equals 2, you get a horizontal line. X equals 4, you get a vertical line. That's always going to be true. But just think about it. If you're ever confused by this, just think about this kind of, these equations here is simply saying, find me the set of points which all share that rule, okay? So moving on then, let's have a look at another graph. Let's have a look at y equals 3x plus 2. Okay, now this is slightly more complex than compared to the first two examples that we're doing, because we actually have a way of linking x and y now. Now, usually you will always be given something that looks like this. Okay, so you'll always be given something which links a y to the x coordinate. But just remember, it's just a way of linking together all of the x and y coordinates. So find me the set of points which follow this rule. Well, what's the rule? It basically says, find me the set of points where the y coordinate is 3 times the x coordinate plus 2. Okay, so if I give you an x coordinate of 5, it basically means the y coordinate will be 3 times that, so 15 plus 2, which is 17. So the y coordinate will be 17. Okay, so just find me the set of points where the y coordinate is 3 times the x coordinate plus 2. Now hopefully you should recognise that this graph just follows the form y equals mx plus c, okay, where the m corresponds to the gradient and the c corresponds to the y-intercept. That's just coordinate geometry, which we've looked at before, okay? So in this case, my m, my gradient, is equal to 3, which basically means every single time I move to the right by 1, I should move 3 up. I should move up by positive 3, okay? So that's all gradient means. It means every single time you move across by 1, it's how many you move up or down, okay? And then the plus 2 just simply corresponds to the height of that line, so how high or low that line is. In this case, it's 2 up, okay? So it should cross the y-axis at 2. So if I just make a quick sketch of this then. So I draw out my coordinate axes like so, okay? And I'm looking for a line which crosses the y-axis at 2, that's what my y-intercept should be. And every single time I go across by 1, I should go up by 3. So I'm looking for a line with a steepness of 3, okay? So that there would be y equals 3x plus 2, okay? So hopefully that makes sense. All right, fine, fantastic. So this is kind of straight lines that we've looked at up until now. The first 3 examples are straight lines. Now let's have a look at something slightly more complicated. Let's look at something like y equals x squared, okay? Hopefully this should be familiar. We've already looked at quadratics quite a lot. So you should hopefully realize this is just a straight, basic, plain, vanilla parabola, okay? So therefore the vertex should be at the origin and it should follow the basic sort of shape like that. So that's the y equals x squared graph, which you need to be familiar with. And again, that's the fundamental parabola, the y equals x squared. If we have a look at the fundamental cubic graph, the y equals x cubed, let's have a look at what that looks like. Okay, so the y equals x cubed will look something like this. Okay, so it's going to basically look a bit like the Loch Ness Monster, as I say to my students. So it's going to look a bit like that, it's curved. Okay, and if you remember, if you've watched the sort of relationship between the fundamental theorem of algebra and their graphs, okay, if you look at the number of turning points on this graph, it turns twice, okay, so you could say it turns here and it turns about there, okay, it'd be a bit more obvious if it's a bit more wavy, which you can get a cubic graph looking like that. So in other words, it turns twice. And you remember that the number of turning points of a graph is always 1 less than whatever the order or the degree of a graph is. So just remember, by order or degree, I'm just simply looking at the highest power. So in this case, the order or the degree is 3, which means I'm expecting it to turn twice. If I look at the last example, the order or the degree is 2, which means I'm expecting it to turn once, which it does. And if I look at the example here, the order or the degree is 1, which means I'm expecting it to turn no times. And you can see it doesn't turn at all on that graph, it's just a straight line. That's also another little check that you can use when you're drawing your graphs, okay? Now let's move on to the trigonometric graph. So for example, if I wanted to draw something like y equals sine x. Okay, so y equals sine x. So if I just draw myself out a set of axes, I'm going to make the x-axis slightly longer. Okay, and in fact, I'm not going to make it negative. I'm just going to make it positive, like so. Okay, and I'm actually just going to draw the sine graph between 0 and 360 degrees, or 0 and 2 pi radians. Okay, and you remember that the sine graph is simply got this sinusoidal shape, so it goes up, and it comes back down, and it comes back up again. So maybe if I make that a little bit more to scale, so something like this. Looks a bit better, okay? And you remember that the range is from 1 to -1. So remember, the range is the set of y values that you can take. And in this case, my domain, I'm going to give it in radians, okay? Because you need to be practiced with using radians. So this is going to be pi by 2. This is going to be pi. This is going to be 3 pi by 2. And this is going to be 2 pi. Just remember, every 90 degrees or pi by 2 radians, something interesting happens. Whether it be reaches a peak, a trough, or goes through the axis, okay? And remember, the sine graph always starts at 0. If I want to draw the cosine graph, y equals cosine of x, then you should get a graph that has a similar kind of shape, so it's that same kind of sinusoidal shape, that up and down nature. However, this time it starts at 1, so it goes up, and it looks like that, okay? In fact, if I draw that a little bit more to scale, it's always more difficult to draw it freehand, but there you go, that's the same kind of shape which it is. So again, the range is from 1 to -1, 0 in the middle, and again, every pi by 2 radians, something interesting happens. So pi by 2 there, pi there, 3 pi by 2, and 2 pi, okay? So you need to be familiar with drawing the sine graph and the cos graph. Of course, you also need to be familiar with drawing the tan graph as well. So y equals tan of x. What does that look like? All right, fine. So y equals tan of x. Again, I'm only going to draw between 0 and 360 or 0 and 2 pi radians. Okay, so it's going to go at 0. Now, we don't actually bother putting any range or any values on the y-axis for the tan of x graph. Reason being is because the range is from -infinity to +infinity. Okay, so the range is all set of real values for the tan graph. Okay, but the graph looks something like this. So it's kind of goes up, then you've got an asymptote, which remember you draw your asymptotes in with a dotted line, okay? And that's going to be at pi by 2 radians. So again, every 90 degrees, something interesting happens. In this case, the interesting thing is it goes through the axis or there's an asymptote. Then you come down, comes through the axis again, and then goes back up, and then you get another asymptote over here. So again, every 90 degrees, something interesting happens. So because it goes through the axis there, that's got to be another 90 degrees or pi by 2 radians on. So that's pi, and that must be 3 pi by 2. And then it comes back up again over here, okay? And that's going to be 2 pi. So you need to be familiar with drawing all of the graphs that I've just drawn on the screen there, okay? So you need to be familiar, obviously, with all of the sine graph, the cos graph, and the tan graphs, all the trigonometric graphs. You need to be familiar with the x squared graph, the x cubed graph, and of course a straight line graph as well. Now there is actually a couple of other graphs that you need to be familiar with, okay? The first one is actually the inverse of the x squared graph, the parabola, which we drew up here. So in fact, I'm going to draw it next to it. Now, I don't know how much you've looked at inverse graphs in the past, but effectively an inverse function is something that undoes something that you've just done. So in this case, if I've taken a value and squared it, remember that's my function, x squared, then the inverse function will be something that takes me back to my original value, okay? So in this case, it's got to be the square root of x, okay? Because if I take a value, square it, the way which I undo that is by taking the square root, okay? And the way which I find an inverse graph is actually very, very straightforward. So if I draw myself out another set of axes, the way which I find the inverse of a function, the inverse of a graph, is by reflecting it in the line y equals x. The reason why I reflect it in the line y equals x is because if you think, if I make a little bit of space down here, we've established that with functions, we looked at that in the last video, a function is effectively a way of getting from an input value, so let's say x, to an output value, okay? Let's say y. Now, just by default, so let's say this is some function of x. Now, just by default, I've just let x be my input and let y be my output. And it nearly always is, can change sometimes, but it nearly always is x is your input and y is your output. Well, I've just said that with an inverse function, you need to go back the other way, okay? So I need to go back the other way. So my inverse function, I'm going to start over on the right hand side and go back to my left hand side. So in other words, I'm going to put a value in that end and it's going to take me back to where I started, okay? And the way which I write an inverse function is with a little -1 in between the f and the x. So the f is my name of my original function, so because my inverse function I just put a little bit -1 after it, okay? But you remember that I've said by default that the input is called x, okay? Which means that whatever goes in here I still have to call it x, okay? And my output by default is always called y, so whatever goes in here my output has to be y. So you notice then that with my inverse function my x and y has changed places. So my x has changed to my y and my y has changed to my x. So just have a think on a graph like this, okay? I'm basically saying that my x's and y's have to change place, okay? Whatever value I put in, so whatever value my original function is my input, now becomes my output. And vice versa, whatever my output of my original function was, now becomes my input of my inverse function. So the way which I make sure that the x and the y values change place is by reflecting it in the line y equals x. Okay, so reflect in the line y equals x. Now, interestingly enough, the line y equals x is actually a self-inverse. Okay, if I take the function y equals x, that literally says whatever my input is, that's also my output. So my inverse function, it doesn't matter. Okay, my output then becomes my input, so it doesn't matter that y equals x. So it's a self-inverse. Okay, so if I take the graph y equals x squared, let me draw that in red. So here's the graph y equals x squared. Let me make that a little bit neater. I've just said that to find my inverse function, I need to reflect this red graph in the blue line. Okay, I need to reflect it in the line y equals x. So if I reflect it in the line y equals x, I should get something that looks like this. So I should get a graph that looks like this and like this. It's kind of a parabola on its side. Now this is getting quite busy, so let me get rid of my original graph and let me get rid of y equals x. So that there should be the graph y equals the square root of x, which I've drawn there on the right hand side. Now the issue is with this graph, okay, by definition of a function, it should be one value in and one value out. So I can't, for example, put 2 in and get a couple of values out. So I can't put 2 in on this side and suddenly get 4 and 5 out on that side. I can't do that, okay? There has to be one value in on this side and there has to be one value out on the other side. That's the fundamental definition of a function, okay? Now it may be that more than one input corresponds to the same output, but the point is, as long as I put one input in on my function, I should only ever get one value out on the other end. Now, if you have a look at this graph over here on the right hand side, the square root of x graph, that is technically true. Okay, the square root of x graph should look like that because I've just followed the technique. I've just taken my original graph, my original function x squared, and just found the inverse by reflecting the line y equals x. However, if I take an input, so my input, say for example something like this, so if I take for example 9, okay, then what that means by looking at the graph, there's 2 points which corresponds to the output. Okay, so if I put 9 into my function, I can either get this value out, which is going to be 3, or I can get this value out, which is going to be -3. Now that violates this definition of a function here. The fact that one value in will only give me one value out. Because in this case, I put one value in, I put 9 in, and I can either get 3 or -3 out. That's wrong. I don't want that, okay? So in order to get around that, I restrict the range of my square root of x function. So actually, by definition, I just get rid of the negative portion of my graph. So the square root of x graph, strictly speaking, only looks like that. It's only the positive portion. Now you could argue, well, why don't we take the negative portion? And you're right, we absolutely could have. But to be honest with you, I would rather work with positive values rather than negative values. So that's just by convention. If you ever see the square root of x graph, it is a parabola on its side. However, we only look at the positive portion of the graph. Okay, and the reason being is because then we don't violate this definition of one value in, one value out. We don't violate the definition of a function. So that there would be the square root of x graph. Okay, so hopefully that makes sense. All right, what other graphs do you need to know then? So we could have y equals 1 over x. Now y equals 1 over x is a really interesting graph. It's actually a hyperbola. You don't need to know it's called a hyperbola, but I'm going to tell you anyway, because why not, okay? And the reason why it's called a hyperbola is because you have two asymptotes on a hyperbola, okay? So in this case, the asymptotes are actually the axes themselves. So it's actually the x-axis and the y-axis. And the 1 over x graph effectively looks like this. So you have a graph like this and a line like this, okay? And the idea of this, because they're asymptotes, so remember an asymptote is a line which the graph approaches, but it never ever reaches. So it gets infinitesimally close. It gets really, really close to it as it goes along, but it never ever touches it, okay? It never ever reaches it. So if you like, it's the limit, all right? So that's what the 1 over x graph would look like, okay? And the reason why they're called hyperbolas is because you have two asymptotes and you've kind of got the graphs going in opposite sort of ways like that. So they're sort of sandwiched between the asymptotes, okay? And that's a hyperbola. Now, sometimes this graph is sort of called a butterfly graph because I guess it does kind of look like a butterfly. If I draw my sort of lines out like that, I guess if you use your imagination a little bit, it kind of does look like a little butterfly. Maybe if I drew a couple of antennas here and a little bit down the bottom there, maybe if you use your imagination, it does look a little bit like a butterfly, but I don't know, it's sometimes called the butterfly graph. That's how at least I remember it. But 1 over x, it looks like that, okay? So what other graphs do you need to know then? Well, you also need to know exponential graphs. Now, I know we haven't looked in detail at exponentials yet. That's coming in the next video, okay? But the exponential graph for the moment will just look like this. Just think of an exponential as just a graph that has a rapid growth. Okay, so it's a graph that looks like this, okay, and that will cross the axis at 1. And again, the x-axis is an asymptote. So in other words, this part over here will carry on growing in that direction. It will get infinitesimally close to this x-axis, but it will never, ever touch it, okay? Now, just like exponentials, just like x squareds and square roots, they're inverse of each other, there is actually an inverse for an exponential. So in other words, if you take a number and you keep on multiplying it by itself, there is an inverse to an exponential, and it's called a logarithm. Now, it just so happens that y equals e to the x. So if you haven't met e yet, we will meet it in the next video. Okay, but e is effectively a special number. It's about 2.718, so it's between 2 and 3, closer to 3 than it is 2. So the inverse of the exponential function is going to be the natural logarithm function, but it's a logarithm, okay? And again, similar kind of idea to before, because these are inverse of each other, I should basically be able to draw the exponential graph in. So I'll draw it in red. So here we go. There's the exponential graph and it crosses at 1, okay? Then the logarithm graph should be reflecting this graph in the line y equals x, the same as before, because it's the inverse function. I'm simply going to take this graph, the y equals e to the x, and reflect it in the line y equals x in order to find what the logarithm would look like. So the logarithm graph, if you reflect it over, will look something like this, and it will cross there at 1. So now if I get rid of the red and the blue line, okay, that's what the logarithm graph will effectively look like. It's just the inverse of the e to the x graph. So there you go. So those are all the graphs that you need to know. So there's 3, there's 4, there's 12 graphs that you need to know how to draw like that. Now what I've basically drawn here are the fundamental versions of those graphs, okay? And the idea is that if you know what all of these graphs look like, and you should be able to draw these from memory now, okay? If you know what all of these graphs look like, you should then be able to get all of the variations of those graphs just by applying some transformations. So that's what we're going to start looking at now. We're going to look at seeing how we can transform these graphs, or any graph that I give you, to get another version of this graph. So these are kind of the plain, vanilla, fundamental versions of the graphs that you need to transform. Okay, so let's think about how we can actually transform these graphs. Now, there are 3 ways that you can transform any graph, and I'm going to give you them now. Okay, you can either shift them. Now, the correct way of saying that is a translation. Okay. And in fact, we're going to look at translations in 2 directions. So they're either going to happen in the x direction, or they're going to happen in the y direction. So that's the first type of shift, or that's the first type of transformation we can have. So translation, otherwise called a shift. So maybe I'll put shift in brackets if it's easier to think of it as a shift. It's literally just sliding things around. Okay, so you can move it vertically, you can move it horizontally, okay, or you can do kind of combinations of the 2 and move them like diagonally and stuff like that. Okay, that's the first type of transformation we're going to look at. Second type of transformation is going to be a stretch. Now that stretch can happen in either the x or the y direction again. So I guess I'm going to form a little table from this. Okay, so I'm going to form a little table. So just put a line down there. Okay, and again, each of these transformations can happen either in the x direction or the y direction. Okay, and then the last type of transformation that we're going to look at is something called a reflection, or a flip if you prefer. Okay, so reflection or a flip. Okay, and again, that can either happen in the x direction or the y direction as well. So let's just finish off my little table. So there we go. Put some lines across there, and then I'll just put a line down the middle just to make sure that we've got the x and the y separated as well. There we go. Okay, so that's my little table, which I'm going to end up filling out there. Okay, now in order to do this, I'm going to come over to GeoGebra Notes. Okay, and we're going to start by creating some graphs. Now I'm just going to have a look first of all at a function. I think a good function which would be good to use would be something like the square root of x graph. So let me start off by just drawing, or let's start off by writing a square root of x graph. So I'm going to add some functions in here, and I'm going to go square root of x. Okay, so there it is, and I'll just move him in the top left hand corner, and I'll just resize this box just to make it a little bit clearer. Okay, fantastic. So here is the idea. Okay, in fact I might make it a little bit smaller. There we go, and I'll position him in the top left hand corner. So that's my original graph, that's my original function that I want to draw. So let's actually start off by drawing what that graph would look like. So I'll put in a graphing calculator, and then I should just be able to drag and drop that straight in there. And you can see over here that the y equals the square root of x graph has been drawn there. In fact, I'm just going to get rid of the label here. Okay, so I'm just going to go into settings, and I'm going to get rid of the label. Okay, so then it's not cluttering up the place. So there we go, there's the square root of x graph. And in fact, I may just fiddle around as well with the style of the line. I'm going to make the opacity, and I'm going to make it slightly thicker. And I'm also going to put this, I'm fine to put it in black, I think. Okay, fine. So that's looking how I want it to look now. So that's the square root of x graph, and I'll just resize it slightly. Okay, now here's the idea. Okay, here's the idea. I want to see how I can transform this original graph here. Okay, I want to see how I can transform this original y equals the square root of x graph. Okay, and just by applying the transformations that we've just looked at. Okay, so let's first of all look at translations. Now, translations are just how we can shift this thing around. So let's first of all look at a translation in the y direction. In other words, up and down. Let's see if we can move this graph here over the left hand side. Let's see if we can move it up and down. Okay, so first things first, what I'm going to do is I'm just going to make a copy of this graph, and I'll just paste it over here. Okay, and I might make it a little bit bigger because now we want to actually work with it. Okay, so I'll just make it a little bit bigger. Okay, and I'll just put a little bit of text in here as well, just to remind ourselves of what we're doing. Okay, so this will be a translation in the y direction. Okay, fantastic. All right, fine. So we want to translate this graph in the y direction like so. Okay, so what I'm going to do, I've got my original graph, f of x here, this is drawn in black, okay, and what I want to do is move it up and down. So I'm just going to play around with this. So let's see what happens, for example, if I take f of x and then I add on some particular value. Let's just say we add on a, just to represent some particular value. Now if I click enter, okay, what I can basically do is I can change the value of a. Okay, so at the moment a is set to 1. If I press the play button, can you see that this graph effectively moves up and down? Okay, so you can see that this graph effectively moves up and down just by changing the value of a. And in fact, if I just make this a little bit wider, you might be able to see the value of a changing. Okay, so you can basically see it's moving from -5 to 5, and you can see that this graph is effectively moving up and down. So what we can say then, is that if we take a graph y equals f of x, okay, so if we take f of x, and if we add on some particular value, that means that the graph is effectively moving up and down. And you can see that on this graph here. Okay, so you can see that this graph is effectively moving up and down. Okay, which is really good. That's exactly what we wanted. Okay, so let me just move this over here then to one side. Okay, and now let's see what happens if we want to do a translation in the x direction instead. So again, I'm just going to actually just make a quick copy of this graph. Okay, and I'll just scooch him over here. So I'm going to make a copy of this graph and move him over here, okay? And I'm actually going to get rid of this. I'm just going to delete that, okay? So let me pause that for a second. Let me delete that, okay? And let me also delete that as well, okay? So now we're back to our original square root of x graph, okay? So now what I want to do is I actually want to give a translation, but this time not in the y direction, but in the x direction as well, okay? So I want to translate it in the x direction instead. In other words, horizontally instead of vertically. Okay, so let me just make that a little bit bigger. So we've got a reminder of exactly what we're doing here. Okay, good. So you notice with the translation in the y direction that what we're effectively doing is changing the value of the function after we put the value through. So we put our value through the function first, then we add or subtract our a from it. Okay, but now what I want to do is actually see what happens if I change the value of x, or change the value of our input, and then apply it through the function. So you notice there's a subtle difference between the order which we're doing things. When we're translating in the y direction, we put our value through the function first and then change it, and that corresponds to moving up and down. When we're translating in the x direction, what I'm going to do is change the value of my input, change the value of x first, and then apply it through my function. Okay? So in other words, in this case, what I want to do is f of x, and then let's say minus a. Okay? So now what happens, if I click play, and maybe I change the settings of this as well. So if we go into settings, change the color, maybe we change it to a nice, let's keep it to red, that's fine, okay? So now what happens, you can see with this graph, is that it should move left and right. So if I now click play, can you see that it is moving left and right as we choose, okay, as we expected. So this is really important, okay? Basically, if I want to move the graph up or down, then what I need to do is put my value through the function first, to do f of x, and then add or subtract a. That's moving it up and down. With this example, if I want to move it left and right, what I'm effectively doing is changing the value of my input first and then putting it through f, okay? So in other words, what I can say is that I've got this, okay? So I've got f of, and it's going to be x minus a. In fact, let me put it in an equation instead, okay? So let me put it through an equation to make it look a little bit prettier. So in other words, I'm taking my value of x first, I'm subtracting a, and then I'm applying it through applying it through f, okay? So this is really important, the order which it's happened. You notice that the other thing which I want you to notice as well is that look when a is positive. So it's going to go positive in a minute. There we go, it's going to go positive now. Look what's happening, it's moving to the right. But look what's happening underneath my square root. I've got x minus something, and it's moving to the right. If I change that to positive, so x plus something, it's moving to the left. So watch that again. When it's x plus something, it's moving to the left, in other words, the negative direction. Whereas when it's f of x minus something, it's moving to the right. That's weird, right? That's really weird. Because if you think, when I was doing it over here on the right-hand side, okay, so let me see if I can move over here. Okay, when I was doing it over here on the right-hand side, so in other words, the f of x plus a, when a was positive, okay, so when a is positive, you can see there it's just gone positive, it's moving up and down. Whereas when a goes negative, so it will go negative in a second, can you see that it's moving down instead, so in the negative direction? So in other words, we've got a little bit of an opposite going on. So let me come back to the table which I've just created and summarize that in here, okay? So if I want to translate it in the x direction, then I'm going to do f of x minus a, okay? And you notice that the x minus a, you think intuitively it should be moving to the left because it's negative, but it's not, it's moving to the right. So in other words, this is a translation to the left, translation to the right by a unit. So the way which I could write that is a0. So when a is negative, so negative a, it's moving to the right. When a is positive, it's moving to the left. So that's really weird. But it's not weird when it comes to the translation in the y direction. There's going to be f of x plus some particular value, okay, so plus a. And that is exactly what we expect. So when it's plus a, it's a translation. Well, it's moving up and down, so it's not moving across at all, but it's moving up by a units. Okay, so that's really important. That's really important to note that. Okay, so hopefully that makes sense. If we want to translate it in the x direction and we want to move it in the x positive direction, we need to take away a from our x. So in other words, it's happening inside the brackets. Okay. If you want to translate a vertically in the positive direction, it's a plus a, but it's happening in the positive direction. So it's happening upwards. Okay, so hopefully that makes sense. Okay, fine. So let's come back to this. So let's now look at stretches, because that was the next one on our list. So we've dealt with translations. We've dealt with how we move the graph left or right, or how we move the graph up or down. Now let's have a look at stretches. So here I have originally my y equals f of x graph. Okay, and I'm going to go with the y direction again. I don't know why I'm doing the y direction first, but I just am. Okay, so now let's see what happens. Well, we saw, didn't we, with our translations, which we've got up here, okay, if we were translating it in the y direction, we had to apply the function to our input first and then do something afterwards. So in this case, adding or subtracting a, okay? Now it makes sense that if you're stretching something, you're basically multiplying it by some value. For example, if I stretch it by 2, I'm basically taking the value and making it twice as big, okay? So it makes sense that I should be doing multiplication with stretches. But let's follow the same kind of technique as we were doing with the last one. So, you know, up here we said, well, okay, if it's in the y direction, so it's happening in the y direction, we apply our function first, then we change it. So in this case, we're adding a for our translation. So for stretch, we should be multiplying. So let's take our function, okay, and then multiply it by some particular value again. So in this case, I'm just going to take a and multiply it by f of x. Okay, so I'm going to do the function first, then I'm going to multiply it by a. So let's see what happens down here then. So if I do a times by f of x. Okay, so let's see what happens here. And let's actually make sure, yeah, let's make it go from 1, let's say. Well, actually, no, let's go from like 0.5 up to, yeah, maybe let's say change it up to 3. Okay, so let's see what happens now. Oops, didn't change at all, did it? Hang on a minute. So we did 3 to 0.5. Click enter. There we go. That's better. So now if I play that, okay, so now you can basically see that the original graph y equals the square root of x in this case, our original function, is basically being stretched in the y direction. So it's almost like somebody's grabbed hold of it and then pulling it up, or in this case, pushing it down. So you notice that when a is positive, when a is greater than 1, you can basically see it's pulling it up by that amount. So if I just pause it there, for example, at 2.85, and let's make it to 3. You can basically see that the original graph has just been grabbed hold of and pulled up, so it's 3 times as big, okay? And it's happening in the y direction. Somebody's literally grabbing hold of it and pulling it up, so it's in the y direction 3 times, okay? Whereas if I make it, say, for example, a half, it's still happening in the y direction, it's just it's made it half as big. So if you like, it's been squashed a little bit down, but it's still happening in that y direction. Just literally imagine a stretch as somebody's grabbed hold of the original graph and either pulled it up or pushed it down. Okay, so that makes sense. Okay, if I set that going again, that makes sense. So what about then if I want this to happen in the x direction instead? So instead of it happening in the y direction, what if I want to change it in the x direction instead? Okay, so we've looked at a stretch in the y direction. Now let's have a look at stretch in the x direction. Well, just like before, we're going to still multiply by some particular value. So we saw with the stretch in the y direction, we were multiplying by a, but we're doing it outside the brackets, okay? So in this case, what we're actually going to do, instead, we're still going to multiply, but instead of multiplying outside the brackets, so once we've applied the f of x, then we multiply by a, that's for stretch in the y direction. Instead of doing that, let's actually multiply by a first. Just like we were doing with a translation, okay? When we did our translation, So when we did our translation, we were doing it in the x direction. It happened to the input first, then we applied our function. So similar kind of idea here. We're still going to do the stretch, so we're still going to multiply it by some particular value, but I'm going to propose that instead of applying the multiple after we do our function, let's apply the multiple before we do our function. Okay, so it's going to be that. Okay, so now let's have a look and see what happens. Okay, so if I go here and if I do f of a times x, okay, let's see what happens. So again, I'm going to change a to be from 0.5 up to 3. Okay, that'll be fine. So let's set it going and let's see what happens. Okay, so let's set it going, see what happens. Okay, so you can basically see now it's still being stretched. Look at the graph, it's being stretched. But what I want you to notice is look at the value of a. So in this case, a, let's actually pause it at 3. Okay, in this case, a is at 3. But have a look. Okay, remember it's in the x direction, so it's almost like somebody's grabbing it from the side and kind of pulling it or pushing it inwards. So it's in the x direction, it's pulling it or pushing inwards in that direction. But when a is equal to 3, so the thing which we're multiplying x by is 3, look at that. It's almost as if it's been squished inwards. Well, how much has it been squished inwards? Look at that point there. 4 has moved to just a little bit over 1.3-ish, okay? So that's basically been pushed inwards by 3, okay? And likewise, if I choose 1, which is going to be about there, that's moved inwards to a third, okay? So it's basically, it's not happening. So if it isn't happening in the x direction, it's the opposite of what you think it should be. So instead of it being pulled outwards by 3, it's actually being pushed inwards by 3 or inwards by a third. Likewise, if I change the value of a to be a half or 1 over 2, can you see it's being pulled outwards so it's twice as far? Look at that point there, that's been moved from 2 right the way out to 4. Okay, so in other words, it's the opposite of what you think it should be. So I'm just going to quickly change this by changing it to 1 over a. Okay, so basically it's the 1 over a is the scale factor. So if a is equal to a half, it basically means it's been pulled out by 2. If a is equal to 3, it basically means that it's been pulled inwards. Basically means it's being pulled inwards or pushed inwards by 3, but it's still happening in the x direction. Okay, so let me set that going again so that you can see it happening in action. Okay, so basically what's happening with the stretches, okay, if the stretches, it's a multiple. If it's a stretch in the x direction, it's being applied to the x, okay, but it's the opposite of what you think it should be. So if a is 3, it basically means it's been squished inwards by 3 times as much. Whereas if a is equal to, whereas if I'm happening in the y direction, so stretching in the y direction, still a multiple, and it's happening to the function itself. So you put the input through the function, then you apply a, the scale factor of a, but it's happening in the same direction you think. So now it's happening vertically. So if a is equal to 2, it basically means it's being pulled up by twice as far. If a is equal to half, it basically means it's been squished down by half. So this is really interesting, okay? Similar kind of thing as what happened with our translations, okay? If the translation was happening in the x direction, it was the opposite of what we thought. If it was happening in the y direction, it made sense, it was intuitive, okay? Same thing with the stretches. If it's happening in the x direction, it's still happening in the x direction, but it's the opposite of what you think it should be. Whereas if it's happening in the y direction, it's exactly intuitive, it's what you think it should be. So let's actually write this in on our table then, okay? So let's bring my table up here. So we've just seen that if you want to stretch in the x direction, you're going to have to change the x. So it's going to be 1 over a times by x, okay? And this is going to be a stretch by a scale factor of a. So I'm just going to put SF for scale factor of a. Okay, so it's going to be a stretch of a scale factor of a. So if a is equal to a half, it basically means it's a stretch. So basically, if I'm multiplying x by a half in here, if that's a half, it basically means it's been stretched outwards, so it's twice as far. Whereas if a is equal to 3, it basically means it's being pulled inwards by 3 times as much. Okay. So what about if it's happening in the y direction? Well, that's nice and easy. Okay, it's just basically taking the function and then applying f of x. Okay, so it's taking the function, then applying f of x. So it's doing f of x first, then multiplying by a. So this is a stretch, okay, with a scale factor of a. Okay, so it's exactly what you think it should be, but I should put which direction it's in. Okay, so this is in the x direction, and this is in the y direction. So basically what I'm doing here is I'm building up a table, which eventually you will just have to learn, okay, but I'm trying to show you why it's true at the same time. okay? So just be aware that if it happens in the x direction, it's kind of the opposite of what you think it should be. So for both the translations and the stretches, okay? Whereas if it's happening for the y direction, it's a bit more intuitive, okay? It's a bit more intuitive. But you notice as well, if it's happening in the x direction, it's the x that we are changing, okay? So we're changing the x. So look here, we're changing the x here, and we're changing the x down here, okay? Whereas if it's happening for the y direction, okay, notice that we apply the function first, then we change the x. So then we change the function. So the a is happening after we apply the function in each of these cases. So just be aware of a couple of things. If we're happening in the x direction, it's the opposite of what you think it should be, and we're changing the x. If it's happening in the y direction, we apply the function first, then we do our thing, but it's exactly the same as what we think it should be. It's intuitive, right? So the last one to have a look at is the reflections. Let's have a look at those. All right, okay, so let's do first of all the reflection in the y-axis, okay? Now, if I want to reflect a value, okay, basically what I'm saying there is I'm making what was positive negative. So if I'm reflecting in the y-axis, what I'm basically saying is that all of these x values has got to be flipped over so it's now on the left-hand side, okay? So if I want to reflect this graph in the y-axis, all of the x values which were positive have got to become negative. So if it was 2, well, the point at 2 has got to move to the point at x equals negative 2. And the point at x equals 4 has got to move to the point at x equals negative 4. So the y values need to stay the same, but the x values need to change. So therefore, because I'm changing the x values, I'm changing the input values first, what I'm going to have to do is I'm going to have to put a negative in here, okay? Because I want to change the x values. I want to make them negative. So because I'm making the x values negative, if I see what happens down here, if I take f of negative x and hit enter, you can see that that graph has effectively just been reflected in that axis. So let me just change the settings. So there you go. You can see what basically what's happened is that all of the x values which are over here have now been made negative. Okay, but the y values have stayed the same. So in order to do that, I need to change the x values first. I need to make them negative. Then I need to apply it through my function. Okay, so let's follow the same kind of principle then, but let's do it with a reflection in the x-axis instead. Well, I'm still going to have to make something negative, but what am I going to have to make negative if I'm reflecting it in the x-axis? Well, are you happy? All the y values now have got to be made negative. So this y value up here, this y value at maybe 1, okay, has got to move down here to the y value of negative 1, but the x values need to stay the same. So if I'm not changing the x values at all, but I'm changing the y values, well, that's going to be achieved by changing the values after I applied them through the function. Because remember, my y values are my outputs. My y values are the values which I get after I applied them through the function. So in that case, the negative has got to be outside. Okay, so if I now put that here, so if I put negative f of x, and if I hit enter, you can see that I get exactly what I want. So in other words, this graph down here has moved down and it's been reflected in the x-axis. So you can see that's exactly what I want, okay? So the black graph up here, which was originally my y equals square root of x, my f of x, I've made them so that all the y values are now negative, and that corresponds to a reflection in the x-axis, okay? So let's come back to our tablet then, and let's fill this in here, okay? So if I want to reflect it, it's nice and simple, okay? If I want to reflect it in the x-axis, well, I need to make the y values negative. So I'm going to do negative f of x, okay? So I need to apply my negative after I've applied it through my function. So that's a reflection in the x-axis. Be careful that you don't say x direction here, because if I'm doing it in the x direction, it actually implies that it's happening horizontally. In other words, a reflection in the y-axis, which is not what I mean. Okay, in this case, it's a reflection in the x-axis. Okay, so make sure you put x-axis. It's different to what we were doing before. Okay. Whereas if I want to reflect it in the y-axis, so it happens in y, then I'm going to have to change my x values to make those negative. Okay? So in other words, I change my x values, make those negative first, then apply them through my function. So that's going to correspond to a reflection in, and again, don't say y direction, say y-axis. Because y direction implies that it's happening vertically. In other words, it's happening in the x direction. That's the x-axis. That's not what I want. It's a reflection in the y-axis. Okay, so that's really important. So there we go. There's a summary of all of the different transformations of graphs that you need to know. Okay, and I can promise you that the more practice that you do with these things, the second nature it will come. Just remember, there's only 3 transformations you can do: translation, stretch, or reflection, and it can only happen in the x or y direction. And just remember, if a translation or stretch happens in the x direction, it's the opposite of what you think it should be. So number one is changing the x values, okay? But it's the opposite of what you think it should be. So with a translation, if it's f of x minus some value, it's actually moving it to the right by that value, okay? Or if it's f of x plus some value, it's actually moving it to the left by that value. Likewise with stretch, it's changing the x, it's multiplying the x by some value, so it's changing the x values. But if it's a half times by x, it's actually stretching it outwards horizontally twice as much. Whereas if it's f of a half times x, or f of 2 times x, it's actually moving it inwards by twice as much. Okay, so it's the opposite of what you think it should be. Opposite of intuitively makes sense. Whereas if it's happening in the y direction, then it basically means that you're doing f of x first, then you're changing the values of the outputs, okay? So f of x plus a basically means you're moving it up by a, f of x minus a means you're moving it down by a. That's intuitive. And likewise for stretches, it's a times by some value. So for example, 3 times f of x means that you're stretching it upwards 3 times as much. A third f of x means that you're squashing it downwards 3 times as small. Okay, and then the reflections, well, they're a bit the anomalies really. They don't really follow the rest. So basically, it's making values negative. So if it's reflection in the x-axis, it means that you're having to make the y values or the output values negative. Okay, hence why you're doing f of x, then you're making it negative. Whereas if you're reflecting in the y-axis, it means that you're making all of the x values negative. Okay, hence why you need to make the x values negative first, then apply them through f of x. Okay, so hopefully that kind of makes sense. Okay, and if you just wanted a nice kind of graphical view of how this works, okay, you can see I've got all of these active here. If you go to my GeoGebra page, Maths Partner, you will be able to see all of these in action. So basically I've got all the translations, I've got the stretches, and you can see the graphs physically moving, and I've also got the reflections happening as well. So you can literally see that the reflections are happening there. What's also nice about this, if you come back over here, so if I come back up here to my original function, okay, so my original function here, if I double click this little dot here next to the function, okay, and double click on it, you can change it to be whatever you like. So let's change it to be, for example, x squared. And if I hit enter, you can see the original graph will change to x squared, and then that will work nicely. Okay, and you can go through and change all of these as well. Okay, so hopefully that makes sense. So yeah, basically if I go up here and I change this graph to be whatever I like, so if I grab the cursor tool, I can change this graph to be whatever I like. So for example, if I double click on that, let's change it to be, for example, x cubed, okay, which I can do, click enter. Then you can basically see that all of these graphs will also change to x cubed, and you can basically see them all moving in unison, or kind of in the correct way that they should be moving. Okay, so all of these graphs have now been changed, and you basically see they're all being reflected and all looking nice. So you can have a play around with this, and you can change it to be whatever you like. So let's change that back to square root of x. So if you're ever not sure, if you're kind of dealing with a question, you're like, I'm not sure how this graph should look after I've done my transformation, not a problem at all, okay, not a problem at all, because basically all I need to do is come here, change my function up here, and then I can see the appropriate change happening over here as well, which is quite good, okay? So I'll also put a link to this particular activity underneath in the description below this video, so then you'll also have access to it that way if you want a nice quick way rather than going to my GeoGebra page. But please have a look at my GeoGebra page as well, because there's some quite good activities there. So yeah, if you want access to this particular activity, if you want to have a play around with it, then by all means have a look in the description below this video. So let's just finish off by looking at some example questions then. So let's suppose I get given this graph here. This is just some function of x, okay? So it could be anything you like, okay? So I mean, I don't actually know what the function is. I just know it is a function. And I know that this is kind of the shape between this particular domain. And I know that it crosses the y-axis at P, which is 0, 3, and it crosses the x-axis at Q, which is 4, 0, okay? And the idea is, I need to see where P and Q end up after I've changed f of x, okay? So if I now suppose that f of x, that I have a new graph that is just simply 3 times the old f of x, okay? Where would P and where would Q end up at? Well, first of all, let's understand what is the transformation that has happened to get from this graph to this graph. Okay, so get from the original f of x graph to 3 times f of x. Well, are you happy that because I'm multiplying by 3, it must be a stretch? Okay, so if it's a multiple, it must be a stretch. And now it's just a case of working out, is it in the x direction or is it in the y direction? Well, are you happy that stretches if it happens outside of the f of x, in other words, I apply my function first, then I do my multiple, then it must be in the y direction. So I know it's a stretch, and I know it's happening in the y direction. In other words, somebody's grabbing hold of the graph, and they're pulling it up vertically, okay, or pushing it down vertically. And how much they're doing it by? Well, they're doing it by a scale factor of 3. Remember, because it's happening in the y direction, it's the same as what you think it should be. So because it's multiplying by 3, it's basically being stretched upwards by 3 in the y direction, okay? So it's a stretch in the y direction by a scale factor, so SF for short, of 3, okay? So that's the transformation that has happened here. So now let's see where P and Q will end up. Well, are you happy that if I'm stretching it in the y direction with a scale factor of 3, P would also be moved upwards with a scale factor of 3. Does that make sense? I literally grab the graph and put it upwards by 3, so stretch, upwards by 3, which means that P is also being stretched upwards by 3 as well. So instead of it being at 0, 3, it's going to be moved 3 times upwards, so it's going to end up at 0, 9. Okay, so it's going to end up at 0, 9. So that's where P will end up, okay? Where will Q end up? Well, are you happy that because it's happening on the x-axis, at the moment Q is sitting on the x-axis, if I pull it in the x direction, in the y direction by a scale factor of 3, I'm not actually going to move Q at all. It's just going to remain fixed, okay? So all the points to each side of the axis, above the axis and below the axis, are all being stretched by 3, but Q will remain fixed. Q is in equilibrium, okay? So in other words, Q will remain at 4, 0, okay? So does that make sense? All right. So what about then if we take y, so we do a different transformation to f of x this time. What about if we take y, the new value of y is f of x plus 4. Okay, so f of x plus 4. In other words, we take the old f of x and then we add 4 to all of our x values, then we apply it through the function. Okay, we'll have a look at this. Okay, are you happy that in this case it's happening to the x values? So therefore it must be in the x direction, okay? But what is it? Well, I'm basically adding or subtracting a value to my x values, which means it must be a translation. Remember, stretch is to do with multiplication and translation is to do with adding and subtracting, okay? So in this case I'm adding or subtracting values, so I know it must be a translation. And I know that because I'm changing the x values, it must be affecting the x direction. So it's a translation in the x direction by, and then I need to work out how much it's being moved in the x direction by, okay? So let's have a think. It's moving by 4 units, you're happy because I'm adding 4, but because it's happening in the x direction, it's the opposite of what I think it should be. So it's not positive 4 units, it's actually negative 4 units. So it's a translation in the negative x direction by 4 units to the left, okay? So 4 units to the left. So I could write all of that if I like, or I could just simply give the translation as translation negative 4, 0. So give it as a vector if I prefer as well. Okay, so either of those is fine. Now let's work out where P and Q will end up at, okay? So because I'm moving the whole graph to the left by 4, let's see where P will end up. So here's P, okay? If I move the entire graph to the left by 4, would you be happy that P will just basically shift to negative 4, 3, okay? So the y value doesn't change, okay? But the x value changes to the left by 4. So instead of being at 0, it's moving to the left by 4, so it'll end up at negative 4. So it'll be negative 4, 3. Let's see where Q ends up. Well, also with Q, it also moves to the left by 4 units. So instead of it being at 4, 0, it'll move to the left by 4 units, so it's going to be at 0, 0. Okay, so the origin. Okay, so Q will end up at 0, 0. Okay, so far so good. Let's have a look at another transformation which we can do to this graph. Let's suppose we take something like y equals negative f of x. So let's first of all work out what the transformation has been done to this graph, okay? So y equals negative f of x. Well, are you happy that because I'm doing a negative in here, it's because I'm multiplying by a negative, it must be a reflection? Now it's just a case of working out which direction or which axis it's being reflected in. So are you happy that because I'm making f of x negative, just remember f of x is my output or my y values, because I'm making those negative, it basically means that if my y value was positive before, okay, it will flip to now become negative. okay? Or if it was negative before, it would now flip to become positive. So in other words, I'm reflecting it because I'm changing all my y values to become negative if they were positive before, or positive if they were negative before. I'm reflecting it in the x-axis. So quite simply, I can just write that this is a reflection. And because I'm making all of my y values, my f of x values, okay, my output values, because I'm making all those negative, it must be happening in the x-axis. Okay, so because it's a reflection in the x-axis, let's come up to our original graph, so up here. And it basically means that Q, I can see straight away, won't change. Because if I reflect Q in the x-axis, because it's literally sitting on the x-axis, it's not going to change at all. So Q is going to remain at 4, 0. However, P will change, okay? So P will change. So instead of it being up here, so instead of it being above the x-axis, it will flip to become below the x-axis. So instead of being 3 units above the x-axis, it'll be 3 units below the x-axis. So it'll be at 0, -3. Okay, so that was a nice, easy one, all right? Let's have a look at another one. Let's suppose we take the same f of x graph, but this time let's suppose we take f of 1/2 of x. Okay, so let's have a think about this then. First of all, what transformation has been applied here? Well, the transformation that's been applied, are you happy? You're multiplying by some value. So therefore it must be a stretch. Okay, just remember, same thing as before. If you're multiplying by a value, it's a stretch. If you're adding or subtracting a value, it's a translation. And if you're making a value negative, it must be a reflection. So here we're multiplying by a value, so therefore it's a stretch. Now, which direction is it happening in? Well, are you happy that I'm multiplying the x values by my stretch? So I'm multiplying the x values by 1/2 in this case. So it must be a stretch in the x direction. Okay, so it's a stretch in the x direction. All right, fantastic. Okay, so because it's a stretch in the x direction, now I need to think, alarm bells should be ringing because it's happening in the x direction. It's the opposite of what you think it should be. Okay, so I think that it should be a stretch in the x direction by a scale factor of 1/2, but it's not, is it? It's a stretch in the x direction by a scale factor, not of 1/2, but of 2. Okay, it's the opposite of what you think it should be because it's happening in the x direction. Okay, so it's not 1/2, it's 1/1/2 or 2. Okay, so it's a stretch in the x direction by a scale factor of 2. So what does that mean then on the original graph? Okay, well, are you happy that anything that's currently sitting on the y-axis is not going to change? So I'm literally just grabbing the graph and just pulling it outwards each direction, each side of the y-axis by a scale factor of, in this case, 2. Okay, so therefore, anything that's currently sitting on the y-axis, such as P, is not going to change. Okay, so P is going to remain fixed at 0, 3. However, Q will move because it's not sitting on the x-axis, on the y-axis. So in other words, Q is going to be stretched outwards by a scale factor of 2. So instead of it being at 4, 0, it's going to move outwards, so it's now at 8, 0. So it's twice as far away from the origin as it was before. Okay, so it's going to end up at 8, 0. Okay, let's just do one final one. So I think I've got another colour. Let's do it in yellow. So I apologise for the colour, but I'm running out of colours here. Okay. So let's first of all do quite a complicated one, or a complex one, more than one thing to it. So y equals, let's do y equals 3, let's make it actually a different number because I think we've already done 3, 5 times f of negative x plus 2. Okay, so there's a couple of things going on here, or 3 things going on here. So let's break it down first of all. Let's first of all have a look at the f of negative x. So you always start with the x value and work your way outwards. So first of all, I need to focus on the negative x part. Okay, so what does the negative x part mean? Well, you're happy because I'm changing the x values. Okay, I'm making them negative. It must be a reflection. So it's a reflection first of all. So I'm making them negative. Okay. And which axis am I reflecting in? Well, if I'm taking all my x values and making them negative, it basically means, if I make a quick sketch, basically means that if I had an x value out here before, okay, it basically gets flipped over, so it's now out here, okay, or vice versa. If it was in the negative portion, it'll be over here in the positive portion. That's a reflection in the y-axis, okay? So it's a reflection in the y-axis. That's the first thing that's happening. Then what's happening? So remember, just work your way outwards. Then I put it through my function, and then next, what I times by 5 or add 2 will order of operations tells me that I would need to times by 5 next, okay? So if I take f of something and times it by 5, so if I'm taking my output and timesing it by 5, I'm basically doing it in the y direction, okay? Now what am I doing? Well, it's a multiplication, so it must be a stretch, okay? So the next thing which comes next is a stretch, and I know it's in the y direction because it's happening my f values, it's happening my output values. And then what's the scale factor? Well, you remember, because it's happening in the y direction, it's intuitive. It's exactly the same as what I think it should be, okay? So in this case, I think it should be multiplied by 5, so the scale factor should be 5, and it is, by a scale factor of 5. Okay, so that's the next thing which happens. Then the last thing that happens, so once I've dealt with all of this business, then I would add 2 at the end. So just think about order of operations there. Then I would add the 2. Well, because I'm adding 2 after I've applied my function, it must be, we'll just think, adding 2 is a translation, right? So it's a translation. And because I'm adding 2 after I've applied my function, it must be in the y direction. So it's a translation in the y direction. Okay, and how much is it moving by? Well, I think it should be by 2 units in the positive direction. And because it's doing in the y direction, not the x direction, it's what I think it should be. Remember, if it's in the x direction, it's the opposite of what I think it should be. If it's in the y direction, it's exactly what I think it should be. So because it's a translation in the y direction, by 2 units. Okay, so by 2 units up, I can say. By 2 units up. If I prefer, I could also give it as 0, 2, give it as a vector if I wanted to as well, but that's fine, okay? So I just need to think then, where would P and Q end up at after I've applied this sequence of transformations? So I'm going to do it in stages, and in fact I'm going to do it over here. So I'm going to do P first of all. So just remember, P was all the way up here at 0, 3. So let's just see what happens after I apply these transformations in stages. So first of all, I need to reflect it in the y-axis. Well, are you happy that because P is kind of sitting on the y-axis, if I reflect it in the y-axis, it's not going to change. So in other words, once I've dealt with the reflection in the y-axis, P is going to stay fixed. So in fact, I might draw a little quick sketch down here, and I'm just simply going to draw P in. Okay, so I'm not going to draw all the rest of the graph in. I'm just going to draw P up here at 0, 3. So that's where it was originally. Then after I've applied my first transformation, it's still sitting there. Okay, so it hasn't changed at all. So P is still sitting there at 0, 3. Okay, cool. Now I can move on to my next transformation. So the next is a stretch in the y direction by a scale factor of 5. So if I now stretch it upwards by 5 units, okay, if I now stretch it upwards by 5 units, let's see what P moves up to. Okay, so if I take P where it was before, and I move it upwards by 5 units. So I literally grab hold of it and move it upwards by 5 units. It's going to move to 0, 15. Okay, it's going to move to 0, 15. So basically P will now move to 0, 15. Okay, and now let's see what happens when I apply the last transformation. So the last transformation is a translation in the y direction by 2 units up. Okay, so I'm moving it up by 2 units. So in other words, I'm taking this point here, and I'm just sliding it up by 2 units. Okay, so in other words, it's going to end up 2 units above where it was previously, so it's going to end up at 0, 17. Okay, so 0, 17. All right, so in other words, the final value of P is going to be at 0, 17. All right, okay, that makes sense. Okay, now let's go back. So P is going to end up at 0, 17. Now let's go back, and I'm going to erase these graphs. I'm going to erase all these points and these graphs here. And I'm going to go and see what happens to Q, okay? So let's get rid of that one. Let's get rid of that one as well. And let's get rid of the original P on there as well. Okay, cool. So let's see what happens to Q now, okay? Well, just remember that Q was all the way out here at 4, 0 to start off with. So that was where Q was originally. So I'm going to put that in. So Q was at 4, 0, all right? So here was Q, I'm going to do it in blue, there was 4, 0 there. Okay, so what's the first thing that I apply? Well, first things first, I reflect it in the y-axis. So I reflect it in the y-axis, it basically means Q will flip over here to be at negative 4, 0. Okay, so Q will end up at negative 4, 0 after I've applied my first transformation. Next transformation is a stretch in the y direction by a scale factor of 5. Well, are you happy that if I stretch in the y direction, I've said before that anything that's sitting on the x-axis won't move. Anything off of the x-axis will move, okay? So if there's a point up here, for example, it will move, all right? But in this case, Q won't move because it's literally sitting on the x-axis. That's the kind of equilibrium point, okay? So anything sitting on the x-axis will not move. So therefore, after I've applied my next transformation, Q will remain sitting here at negative 4, 0. So Q is still at negative 4, 0. So far it hasn't changed from the last transformation. Okay, so now let's think about the last thing. Well, okay, this one is just a translation in the y direction 2 units up. So I'm literally taking the point and just shifting it up by 2 units. So that will move, okay, so that will move up here. So it will still have an x coordinate of negative 4, but the y coordinate will be 2 above where it was previously. So it'll be a negative 4, 2. Okay, so that will be the final position of Q. So Q will end up at negative 4, 2. Okay, so with these types of graphs, okay, always first of all just have a look at the notation and figure out exactly what transformations have been applied and in what order. Then just make yourself a quick sketch like I've done over the left hand side, particularly if it's multiple transformations, and just think, where will this point end up at after I apply each transformation in that order? Okay, and then you'll be away, and that's really as hard as it will get.